I will have 2 lectures, and both of them will be about basics of magnetism. During first course here, I will talk about general information about magnetism, definitions, units, terms, explanations, and some important parameters in magnetism. And in the second part, I will talk about types of magnetism. For example, paramagnetism, Curie or Curie-Weiss type of paramagnetism, quantum mechanical treatment of paramagnetism, and also ferromagnetism, exchange interaction, spin waves, magnons, and also antiferromagnetism, ferrimagnetism. We will see all these types of magnetism during the second part. And finally, I will finish with the magnetic anisotropy in single crystalline materials and also magnetic domains, which are very important for data storage industry. For further reading, you can visit Introduction to Magnetic Materials, which is written by Kalite. This is very pedagogic magnetism book. I strongly suggest this one. And Physics of Ferromagnetism, written by Chikazumi. And Magnetic Materials, written by Nicholas Spalding. This is very, let's say, short one. And also concerning exchange interaction, spin waves, magnons, you can also visit Introduction to the Physics of Charles Hitler. Okay, so why do we need magnetism? Is magnetism important or not? Of course, magnetism is very important. We pay lots of money every day, every year, billions of dollars. So, for example, we already use read heads for magnetic hard disk drives. We store the information in magnetic materials, and we read the information via magnetic materials. This is very important. If you have computer or if you have laptop, so it means that you are using some magnetic materials and you paid for them. And this is magnetic random access memory introduced by IBM recently, but it's not in the market now. But soon we will start to use this one also. And these are the unsuccessful parts of magnetism, but many people is working on this. Spin field effect transistors and spin light emitting diodes. This will be, this type of devices will be much faster compared to the semiconductor-based devices, and they will also consume less electricity. But they are still under investigation. And of course, in the future, magnetic nanoparticles will be used in cancer cell detection and destroy. But of course, this is also under investigation, but many people concentrated on this. For example, you have nanoparticles, magnetic nanoparticles. You cover these magnetic nanoparticles with some poison, and finally you cover them with some proteins which cancer cells like. And then you send them these nanoparticles into the body, and via external magnetic field you can align them into the cancer region. Then when the cancer cells eat these magnetic nanoparticles, you can easily destroy them. But important parameter is that you can kill the cancer cells selectively without destroying any other organs. And this is imaging. I will talk about all these things during my lecture, Applications of Nanomagnetism and Spintronics. I think it's on Thursday. I will not give details here. Okay, so short history about magnetism. This is iron oxide, or we call it magnetite, iron 3 oxygen 4. This is first magnetic material used by people. And William Gilbert done the first systematic work on magnetism and published these results in a book on the magnet in 17th century, beginning of 17th century. And very important step in magnetism done by Hans Christian Ørsted he discovered that an electrical current produces a magnetic field. This was a very huge discovery in magnetism and changed lots of things in the world. And after this discovery, first electromagnet appeared. So if you can produce magnetic field via electrical currents, then you can produce electromagnetism. Am I speaking very fast? Can you follow me?
Yes.
Okay. If you have any questions, you can stop me and ask your questions, okay? We can discuss also during lecture. And another important, very, very important step done in 1988, discovery of giant magnetizing resistance. I think you know this one because this is awarded by Nobel Prize in 2007. This GMR effect is the basics of magnetic hard disk drives. Okay, very important effect. Okay, so let's start with the magnetic poles. We know that from high school years, if you have a magnet bar, if you have a magnet, it means that you have two poles. One is N pole, the other one is S pole. If you divide this magnet bar into two parts, then again both of these parts will have N and S poles. Okay? And we also know that N pole will repulse another N pole, and N pole will attract another S pole. And this is discovered by Charles Coulomb and John Michel independently. Okay, so how to define this attraction and repulsion forces between magnet poles? This is given by this formula. This P shows pole strength. Where is it? Yeah, here. Pole strength is given by P1. For example, you have two poles here. This is P1, for example. This is P2. P1 and P2 are always equal to each other for the one magnet bar. But if you have another magnet bar, of course, pole strength of different magnet bars will be different from each other. Okay, let's come to this attraction and repulsion forces. This force is given by P1 times P2 divided by D squared. D is the distance between these two poles. And this is given in CGS unit system, and the unit is din. It is important to remind you here that the units and terms and also some symbols are very, very mixed in magnetism. Some people use, for example, M for this P, and some people use SI unit system, some people use CGS unit system. During the lecture, I will try to give both unit system for each equation or each term, okay? And in reality, the magnetism community usually uses CGS unit system. For this reason, I will concentrate on the CGS unit system. In SI unit system, we will only add this parameter here, 1 divided by 4 pi, mu 0. Mu 0 is the permeability of free space. And in SI unit system, of course, the unit of force is given by Newton. And there is always conversion between CGS unit system and SI unit system. For example, 1 Newton is equal to 10 to 5 din. Okay? So, what is magnetic field? We hear this term in many times. What is magnetic field? For example, you have a magnet bar, okay? And if this magnet bar has two poles, N and S, okay? If one of these poles feel any force or any effect on itself, this means that they are located in magnetic area or magnetic field. Field means area. It's coming from the English, okay? So if you are talking about magnetic field, it means that in this field, in this area, all magnet poles feel some force on their itself, okay? And we have two main sources to produce magnetic field. You know the electromagnets or superconducting magnets, right? But there is another source which can be produced by magnetic field can be produced by magnetic poles. if you have a magnetic dipole, for example, you have a magnet bar, we know that we have field lines coming from N and they go to S. Okay? These field lines are the source of magnetic field in a magnetic dipole. But electrical currents can also produce magnetic field. And how to define magnetic field? For example, here I have P1 and this is P2. This pole will produce force on this via these field lines. And the false strength of this pole is given by P1, and distance is the length of the magnet bar, and P2 is this one. So finally I can define this one as H, magnetic field. The symbol of magnetic field is H, and in some books, in some papers, in some lectures, people use B for the magnetic field. But this is not the correct use. I will concentrate on this later on. Okay, so unit of magnetic field is Ørsted in CGS unit system. What is in SI unit system? Tesla, that's right. Okay, and one Ørsted is given by one line of force per square centimeter. For example, here you have many force lines, and in 1 square centimeter, if you have one line of force, this is given by one Ørsted. Okay? And in SI unit system, this is given by this parameter, and the unit is ampere per meter in SI unit system. Okay, I have told you that we can produce magnetic field via electrical currents. So for example, let's have a look solenoid. Who knows solenoid? What is solenoid?
Metal conveys
rolling bar. Rolling.
Like coil, right?
Yeah.
You have conducting wire, okay,
Yeah.
and you make pipe or tube from this conducting wire, and when you drive current, then you produce magnetic field inside of the coil, okay? This is solenoid, and the magnetic field in the center of solenoid is given by N times E divided by L. N is, hocam aslında tahtamız olsa iyi olurdu ama böyle bir imkanımız yok herhalde. Okay, N gives a number of turns, okay? Number of turns of the solenoid, and I is the current which you drive, and L is the length of the solenoid. For example, you have solenoid like this, L is the length of the solenoid. Maybe you can understand why people produce electromagnets, this very small area, this very big wells. So you have to increase number of turns in order to increase the magnetic field. You have to increase the current, okay? But you have to decrease the length. For this reason, you need very big wells and very small length for producing electromagnets. And maybe you can also understand why people use superconducting electromagnets, because with superconducting electromagnets you can drive lots of currents compared to copper wires, okay? So this is ampere per meter, unit of the magnetic field in SI unit system. This field is produced by the solenoid, and this field is given by 4 pi N times I divided by 2L in CGS unit system. So only this 4 pi and 10 is coming to this equation given in SI. Okay, let's compare some magnetic fields. For example, what is the magnetic field produced by the Earth? It is given by 0.35 Ørsted, but in Gebze, okay, close to Istanbul. What about here? What about the poles? What about the equator? Any idea about it? What is the magnetic field of Earth? For example, in the poles, North Pole, South Pole, for example, or in Ecuador. Any idea? It will be smaller or higher in the poles, magnetic field of Earth. Kutuplarda. Any idea? It must be higher. Why?
You get closer to the center of the Earth.
It's around 0.6, for example, in the poles. It is due to the magnetic field lines. You can see here. Here I have a magnetic bar, for example. Here N pole and S pole. You can easily see that the magnetic field lines are very condensed around the poles. Okay, for this reason we may expect high magnetic fields at the poles of Earth. And for example, in the toys or in advertisement things which you put them on the refrigerator, for example, the magnetic field is around 5,000 Ørsted, and you can produce 2 Tesla or 20,000 Ørsted by using a powerful electromagnet. If you use superconducting magnet, then you can reach up to 5 Tesla, 9 Tesla, 14 Tesla, or even higher, okay? And the only difference between this electromagnet and superconducting magnet is that this formula, okay? You can drive very high currents. For this reason, you can produce very small electromagnets, but you can produce very high fields. So instead of increasing number of turns, you can increase the current, okay? This is the advantage of superconducting electromagnets. Okay, the relation between Ørsted, Gauss and Tesla. In vacuum conditions, 1 Ørsted is equal to 1 Gauss. But I will come to this later on. Ørsted is given for the magnetic field, and Gauss is given for the magnetic flux density, B, okay? And B is only equal to magnetic field in vacuum conditions. I will come to that point. And 1 Tesla is given by 10 to 4 Gauss, and Tesla is used in SI unit system, as we discussed this at the beginning. Okay, what is magnetic moment? Maybe you hear many times when you read papers or textbooks, what is magnetic moment? And what is the magnetic moment of electrons? What is the magnetic moments of atoms? We will discuss these things now. For example, you have a magnet bar, length is L, and you apply external magnetic field with some theta angle, okay? And this pole will feel force on it, which is given by P times H. This is coming from this formula. Okay, P times H. Force is given by P times H. So, this pole will also feel some force, but the direction of the force will be opposite to that one, okay? And finally, if I write the moment of this torque acting on this magnet bar, I will get this contribution, and it will be given by P times HL times sinus theta. Here I will do some assumptions. For example, let's assume that I applied just 1 Ørsted, okay? Then H is 1, okay? And let's assume that the theta is 90 degrees, okay? So it is orthogonal, let's say. And sinus 90 degrees is equal to 1 again. Finally, the magnetic moment of this torque will be given by P times L. P is here, L is here. P is the pole strength of the magnet bar, L is the length of the magnet bar. Any question here? And if there is no frictional forces acting on a magnet, this work done by this torque is reversible, so it will give us the potential energy. And potential energy is given by this formula, minus P times L times H times cosine theta. We know that this P times L given by mu, magnetic moment, and P times L is given by mu. Finally, I have potential energy minus mu H cosine theta. I can also write in this form this scalar product, minus mu times H. This is very important parameter, very important formula, and you will need this expression every part of the magnetism, potential energy. In some books, people use only energy, E symbol, but here I use E subscript P, EP, potential energy. Okay, the unit of magnetic moment in SI unit system, Weber times meter. Meter is coming from the length, Weber is coming from the pole strength, and the unit of potential energy is, the unit of the energy is given by erg in, right? In CGS unit system, are you here? Am I going very fast? I have to, I would like to show you all transparencies, but if I'm very fast, please tell me, okay? So, the unit of energy in CGS unit system is erg. I think you have heard about this. And the unit of magnetic field in CGS unit system, what? Ørsted, right? If I take magnetic moment from here, then I will get erg per Ørsted, right? And in order to make a short notation, I will call it as EMU, electromagnetic unit of magnetic moment, okay? But this EMU is not a unit, just abbreviation, okay? It is not unit. Electromagnetic unit of magnetic moment means erg per Ørsted in CGS unit system. Any question here? Then I will continue. Okay, so let's come to the real magnetic moment. For example, here I have a closed loop, and I have a current in this closed loop. Current is given by I. Then with right-hand rule, I will have magnetic moment along this direction produced by the current in this closed loop. And this magnetic moment will be given by current times area of the loop, okay, A. And then I can get another unit for this magnetic moment is given by ampere times square meter, okay? So, for example, who knows PPMS devices of quantum design? Or who knows SQUID devices of quantum design company? Okay, these devices measures magnetic moment or magnetization, and they give you two options for the unit of the magnetic moment. One is ampere times square meter. The other one is EMU, means that erg per Ørsted. You can choose both of them, okay, it's possible. One is in SI unit system, the other one is in CGS unit system. It depends on you, but as I told you, magnetism community usually uses CGS units. Okay, what is magnetic dipole? You can understand from the name, we are talking about two poles, okay? Dipole means two poles. But of course, not same poles. If we are talking about dipole, we will talk about opposite poles. It means that we will talk about N and S, okay? If you have a magnetic moment, if you have a magnetic atom, if you have a magnet bar, it means that you have magnetic dipole. And there are field lines coming from N and they are going to S pole. Okay, let's come to the definition of magnetization, which is given by magnetic moment per unit volume. And this is also called as volume magnetization. Okay? And the unit of magnetic moment in CGS is EMU, and the unit of volume is cubic centimeter. So finally, I have EMU per cubic centimeter for the magnetization. But, for example, you heat your material. For example, this is a magnetic material, and you would like to measure this material at different temperatures. For example, you cool this material to 10 Kelvin, for example, or you heat this material up to 1000 Kelvin, for example. Then, at high temperatures, this material will expand, right, due to thermal energy. And at low temperatures, this material will shrink, okay? Then, the volume will change, right? So then this definition will be meaningless. Then I have to find another definition for the magnetization, which must be temperature independent. For this reason, we define specific magnetization or mass magnetization, which is given by magnetic moment per gram, okay? Mu per m. And we know that mass is given by density times volume. So then here I have mu per volume, which is given by m here. Then I will put m here. So finally I have the unit of mass magnetization or specific magnetization, which is given by mu per gram. Okay? Any question here? Please.
Is it common that there's another unit, ml per square meter or per square centimeter?
In some papers or in some books you can find this type of definitions, but this is not the real definition. If you have EMU per square centimeter or square meter, you have to, of course it cannot be square meter, it must be square centimeter if you are giving this EMU. For example, if you have EMU per square centimeter, it means that you only divided magnetic moment by the area, okay? You have to also divide this magnetic moment by the thickness of the material, okay? This is important. Then you will get real magnetization. EMU per square centimeter is not the real unit of real demonstration of magnetization, okay?
But for some film, some in some single layer,
Yeah.
molecular layer,
Yeah.
it's quite hard to get the volume or the density of the film. So the only limit you can use is the depth square centimeter.
You are right. Sometimes it is very difficult, then people understand this. But if you would like to, for example, calculate the magnetic moment of each molecule or each atom, then you have to provide this one or this one, okay? Okay, but if you are dealing with very small particles, for example, if you are talking about 1 unit cell, or if you are talking about FF atoms, or if you are talking about 1 atomic layer, especially in ultra-thin films, then we have 4 magneton, okay? Because magnetic moment will be very small for the atoms, and 1 more magneton is given by 9 times 27 times 10 to 21 per Ørsted or EMU. I will come to that point later on, but it is better to keep in your mind. Okay. Hocam ne kadar zaman kaldı?
15 dakika.
14 dakika var.
Let's talk about the magnetic flux density. At the beginning of this talk, I have told you that people mixes magnetic field and magnetic flux density. Means that H and B. H and B are not the same things, okay? H is used for the magnetic field, external magnetic field. B is used for the magnetic flux density or magnetic induction, okay? It is not the magnetic field. And this magnetic flux density, B, is equal to external magnetic field plus magnetization of the material, 4 pi m, okay? But in vacuum conditions, there is no material. If there is no material, it means that this 4 pi m is 0, okay? Then B can be equal to H. But this is only valid in vacuum conditions. Is it clear?
No, I'm sorry.
Please.
In the beginning, you explained that B and H in different things
Yes.
in terms of the meanings.
Yes.
I mean, B explains something different than H. But now you say in vacuum conditions, the quantity is equal, but still meanings are different. Or am I right or not?
Still, there are meanings, different things. But if you add any magnetic material, then it will be quite different. Let me explain here. For example, here you have a rectangular shape. Let's consider that this is a magnet bar, okay? And you apply external magnetic field to this material, and you magnetize this material. Finally, this material earns this magnetization, 4 pi m, okay? You have magnetic field lines, because you have electromagnet, you apply magnetic field, and you have field lines. You produce magnetization here. Once you magnetize your sample, this material will give additional field lines. See, the total number of field lines produced by external magnetic field and 4 pi m will give us the magnetic flux density, okay? This is the magnetic flux density. And only at vacuum conditions, if there is no material, if there is no magnetization, then B will be equal to H, okay? This is very important, but in physics, in other physics-related disciplines, usually B is used instead of H, but this is not the correct usage. And there is a paper, it is around 35 pages, explains this differences between B and H. Okay, so the unit of B is Gauss, the unit of magnetic field is Ørsted, and the unit of 4 pi m is again Gauss, not the unit of magnetization, unit of 4 pi m. And as I told you, in free space or in vacuum conditions or in air, magnetization is 0, then B is equal to H. So gas in this case can also be used for magnetic field. And this is the definition given in SI unit system. Okay, let's come to magnetic susceptibility. Magnetic susceptibility is very important parameter in magnetism. For example, you would like to define a material, whether it is paramagnetic, ferromagnetic, antiferromagnetic, ferrimagnetic, or superparamagnetic. You have to measure susceptibility or magnetization of the material against the magnetic field, against the temperature, okay? This gives us the material properties. For this reason, susceptibility is very important. For example, sometimes susceptibility is positive, sometimes it is negative, sometimes it is very high, sometimes it is very small, for example, in diamagnetic materials. Susceptibility is given by M divided by H. This is also called as volume susceptibility because this is volume magnetization, okay? The unit of this volume magnetization is given by EMU per cubic centimeter, and the unit of magnetic field is given by Ørsted. And this is mass susceptibility. I explained why I use this mass magnetization and mass susceptibility. So, which is also given by volume susceptibility divided by density of material, and the unit is given here, mol per Ørsted times gram. And this indicates that susceptibility indicates that how responsive a material to a magnetic field, external magnetic field. This is the indication of susceptibility. And we have another term, magnetic permeability. In this scientific case, it is not commonly used, but for the electricity people, it is very important parameter. In order to design transformators and other electricity-related devices, you have to know the permeability of the material which you use. So this is given by magnetic flux density divided by magnetic field, okay? And since this B, magnetic flux density, is given by magnetic field plus 4 pi m, if you put this one here, then finally you will get magnetic permeability 1 plus 4 pi volume susceptibility. And this indicates how permeable the material is to apply external field. Are you tired? Now we come to the most important part of this lecture. So, what is the origin of magnetic moment in the atoms? Okay, in the atom we have nucleus, we have electrons around the nucleus. They are traveling in certain orbits, right? And what do you expect? For example, I have a nucleus here, and then I have electron, and this electron is traveling around this nucleus. But the velocity of electron is very high, very fast, okay? So, can I consider that a current is traveling here, right? Because electron is traveling very fast. What is current? Current means that charges are going from one place to another place, right? So the charge, electron, is traveling here in very fast way. So I can consider that there's a current here. And this is closed loop. And I know that closed loops carrying electrical currents can produce magnetic moments, right? This is the origin of magnetic moment, orbital magnetic moment of electrons. And electron has another movement. It also rotates around itself, like this, called as spin movement, right? Spin. So this movement also produces a magnetic moment. So electron has two contributions to the magnetic moment. One is coming from orbital motion, orbital magnetic moment. The other one is coming from the spin motion of the electron, spin magnetic moment. Okay, so the magnetic moment from the orbit is given by the E times A, and the current here, current of the electron traveling in the orbit, is given by E over C. This is the charge of the electron and velocity of electron divided by the circumference of the orbit. In CGS unit system, in SI unit system, it is given by this formula, and A will be given by pi r squared. So this is mu orbit. This is the current of the electron in the orbit. This is the area of orbit. Finally, I have this formula for the CGS unit system. This is given in SI unit system. I know that in the Bohr atomic model, this angular momentum of the electron is given by n times h bar, right? H divided by 2 pi. And it is also equal to m times v times r. If I take this Vr from this formula and put this Vr here, okay? Can you follow me? If you take this Vr from this formula and put it there, then finally you can get orbital magnetic moment of the electron, which is given by E times h divided by 4 pi mc. There must be also n here. There is an n here, but if n is 1, it means that the first Bohr orbit, the nearest orbit to the nucleus, right? And we know that spin also has magnetic moment, and which is calculated. This is also equal to this formula. And please look at this one. This is also an important point. EH divided by 4 pi mc, and this is same, okay? So the orbital magnetic moment for the first Bohr orbit is equal to spin magnetic moment of electrons. And this is constant and valid at every conditions for every material, okay? Then this relation is called as Bohr magneton. This one, Bohr magneton. Bohr magneton means that for the first Bohr orbit, orbital magnetic moment of electron is equal to spin magnetic moment, okay? And which is called as Bohr magneton. Okay, I have around 5 transparencies. So what about the magnetic moments of atoms? Now I have told you magnetic moment of one single electron traveling around the nucleus. But in atoms there are many electrons, many orbits, right? So what about them? So the total magnetic moment of the atom is given by the total number of electrons and their contributions to the orbital magnetic moment and spin magnetic moment. But we know that due to Pauli exclusion principle, in one orbit, electrons can have one spin up position and one spin down position, okay? Then they will cancel each other. So they will cancel the spin and orbital magnetic moment, right? For the closed shells. If we have unpaired electrons, okay, in some orbits, if we have unpaired electrons, these unpaired electrons will give rise to net magnetic moment for the atom, okay? This will define the net magnetic moment of the atom. So, the source of magnetic moments in the atoms is unpaired electrons, okay? So, diamagnetism, very important magnetism type. It is very small, but very important because it happens in every material. For example, you have a ferromagnetic material, you have an antiferromagnetic, ferrimagnetic, superparamagnetic material, whatever. Or even some materials are not magnetic. But every material in the world has diamagnetic contribution, okay? When they exposed to external magnetic field. So diamagnetism is very important. It is very small, but it occurs at every material. So the classical theory of this diamagnetism done by Paul Langevin in 1905. And what he considered that, for example, maybe first of all I should define this. There is a diamagnetic atom, okay, this is something else, and there is a diamagnetism. This is another thing, okay? Diamagnetic atoms means that all electrons in the orbits have their pairs, okay? So net magnetic moment of atom is 0, okay? If atom has 0 magnetic moment, this is a diamagnetic atom, okay? But diamagnetism is something else. For example, you have an electron, it is traveling in the orbit. If you apply external magnetic field, due to this external magnetic field, there will be opposite magnetic moment, okay? This is diamagnetic contribution to the magnetic moment. So electrons has two intrinsic contribution to the magnetic moment. One is spin contribution, the other one is orbital contribution. And external contribution is produced by the external magnetic field, and it is opposite to the applied external field. Okay? Bitti mi hocam? Let me show you here. This is the magnetic moment produced by the external magnetic field, and here I have negative sign because the magnetic moment produced by the external field is opposite, right? And if the external magnetic field is zero, then magnetic moment produced by the magnetic field, it means that diamagnetic contribution to the magnetic moment is zero. And this is the susceptibility of the diamagnetic materials. What you can see here that the susceptibility of diamagnetic materials is temperature independent, okay? It is constant with temperature, and it has minus sign. Here I have a demonstration to show this effect. You will apply, for example, magnetic field in this direction, you will apply magnetic field in this direction, and magnetic moment will occur in opposite direction, okay? This is a frog in a jam, okay, in vacuum conditions. There is no water inside, and if I apply external magnetic field along this direction, then the frog will be elevated, okay? This is called as magnetic levitation, and you can see many videos in internet. Okay, so what I have told you that, please look at this one. If I increase magnetic field, magnetic moment will increase in opposite direction here. I will increase magnetic field, magnetization or magnetic moment will increase in opposite direction. Again here, like this. And if I change the temperature and measure the susceptibility of diamagnetic material, I will have negative susceptibility, and then the susceptibility will be constant. Now, my question comes at that point. How we can measure the magnetization or magnetic moment? Any answer?
Elevation.
Not exactly. For example, you would like to calculate or measure the magnetic moments of atoms, for example. The best one is squid magnetometry. The other one is 10 times less sensitivity, VSM magnetometry. There is a MOG magnetometry, magneto-optical carrier effect. There is a XMCD method or XRMS method. You can also calculate the magnetic moment or measure magnetic moment via this methods. I will shortly show you. For example, this is squid magnetometry. You have a helium diva here, and computer control software, and also electronics and some pumps. So what you have a superconducting magnet here. In quantum design devices, it's around 5 Tesla. And then you put your sample here, apply magnetic field along this direction or this direction. Then here you have pickup coils, and you send them to the squid. Then you amplify your signal. So you measure the total magnetic moment, what you have in your material, and it is very sensitive. Sensitivity around, let's say, 10 to minus 7 usually, EMU. And you get information from the film and substrate. Sometimes it is disadvantage. This is quantum design DC squid, and this is squid from NIST. And this is also VSM magnetometry. Of course, there are many companies produces VSM magnetometries. This is produced by the quantum design. In VSM magnetometries, you have field range from 0 to 9 Tesla, or sometimes even 14 Tesla. And the sensitivity is 10 times less than squid. but the temperature range is very high, from 2 Kelvin to 1000 Kelvin you can measure. You have here linear motor in order to vibrate your material, and this is the sense coils, pickup coils. Here you have pickup coils, and this is also cryo cooler in order to cool the superconducting magnet and the material. And this is mock magnetometry. My time is finished, so I will finish with this one. What is mock magnetometry? This is very old method to measure the magnetization. The disadvantage is that you cannot measure the magnitude of the magnetization. Mock magnetometry does not give the magnitude of the magnetization. Okay, so you cannot get the EMU per cubic centimeter. It is not possible. But the advantage is that it is very fast and very cheap compared to SQUID and VSM magnetometries. And you can also get information from very thin films. This is also an advantage compared to SQUID and VSM magnetometries. Thank you very much for your attention. It's okay, Yasin. Hocam break verelim. Ne kadar zamanda bitirdin? Ne kadar kaldı?
You are almost 10 minutes over the time, so we have 7 minutes to go for another one.
Ne zaman başlayacağız yani? Start at 10 o'clock.
At 10 o'clock, yeah. It's 7 to 10 now. We have 7 minutes to break.